just saying I have a graph isn't in and of itself very descriptive. And I would like to look at some categories, families of graphs, so that I can talk about particular kinds. Now, we've already seen things within a graph, but those things can be graphs in and of themselves. A path. What was our definition of a path? I promise you all wrote it down because I've said it several times. What's our definition of a path? Ben. Okay, a walk with no repeated vertices. Okay, well that means it's got to look like starting vertex, next, and since nothing's repeated, it can't go back on itself. I'm not going to be able to repeat an edge since I can't repeat a vertex. Well, that basically means that a UV path looks like that, right? It could be within some other graph, but if I grab you and I grab me and I stretch them out, this is what it looks like. So we're going to define a path, pk, a path of length k. I just realized that I wrote the vertices instead of writing it, so we'll just do that. There we go. I didn't write circles for all the little vertices. Don't tight. So no matter what path I'm talking about, this path has k edges. Path of length k, pk. Each edge goes between sequential vertices. vi plus 1. That's an edge. Hang on a second. I've made a cardinal error. This is the beginning of chapter 1, section 3. Somebody open a textbook. Look at chapter 1, section 3 for me. Tell me about their path of length k. Screwed up. See if we can catch what I screwed up. I wrote a path of length k as pk. They write a path of order k. Which means I have one too many vertices. And we see it right here. They label the vertices vertex 1 through vertex n, not vertex 0 through vertex n. So I want to chop this one off. Instead of writing length k, I want to write order k. So we go from v1 to vk. This path has length k minus 1. So our k here refers to the order, not the length. I apologize. Because I want to count by vertices at this point, so I want to count by order. What's our definition of a cycle? So it's very similar to a path, except it is closed. There. A cycle looks like a ring of vertices. A cycle of a cycle of order 3 is a triangle. A cycle of order 4 is a rectangle. A cycle of order 5 is a pentagon, and so on. A cycle of order k is k vertices in a ring. So if I label the vertices v1 to vk, then my edges, not vertices, edges. I don't know what it is today. I apologize. It hasn't been that long of a day, and I'm still all my fault. So notice I get an edge from vi to vi plus 1, and then I wrap around. We could think of this as counting mod k. Only instead of 0, we're using k this time. So paths and cycles were part of other graphs, but I can think of them as a whole class of graphs unto themselves as well. Questions? So I have a path, pk, k vertices. I have a cycle, ck, k vertices. What do you think the adjective complete could be used for to describe a graph? If I say this is a complete graph, what's the adjective complete mean to you? It's finished. Okay. If a graph is finished, then I can't put anything else into it. It's done. It's as big as it can be. Big is size. Size is number of edges. So I'm going to call a graph complete if every pair of vertices is adjacent. So if I have n vertices, I know I switched from k to n. There's a reason for that. If I have n vertices, then I want to use every possible pair of vertices that are distinct from one another and put an edge between them. Okay. An example. A path of order 2 is complete. There's only one possible place to put an edge, and I put it there. What if I give you 3? What's your graph going to look like? Triangle. What if I give you 4? Say again? Unfortunately, no. There's more edges than that. I've got 4 items. I'm taking them 2 at a time. I remember discrete combinations, 4 choose 2. How many ways are there to get 2 objects out of this set of 4? There are 6 edges. So I end up with a square. But then I'm missing things, aren't I? I'm missing this one. And I'm missing that one. There are actually 6 pairs, 6 edges here. We're going to call these graphs complete. We're going to call them K, K2, K3, K4. What's K5? But wait, there's more. What else do I have in addition to those pentagon edges? I got the pentagram on the inside, don't I? 1, 2, 3, 4, 5. Wait a minute. Kn has n vertices. And how many edges? What fills in that blank? You all are going to hate me for this. Chapter 6, Section 3, discrete math. N factorial would give me all the possible things. So 4 factorial is 24. I only drew 6. I have a lot more trouble drawing 24. Okay, so 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, there's a formula for that. Summation, well, not 1 to n, summation of 1 to n minus 1, right? So I'm adding all the numbers from 1 to n minus 1. I know I did that formula in discrete. Matter of fact, I did that formula in calc as well. But you're exactly right, Reese. That's where I get that number from. That's the summation from 1 to n minus 1. And how do we know it's the summation from 1 to n minus 1? Think about the vertices one at a time. This one has to connect to 2 others. But this one's already connected to that one, so it only has to connect to 1 other. This had to connect to 3 others. Now this has 2 it's not connected to, and this has 1 it's not connected to. So starting at vertex 1, it has n minus 1 others to get to. Then vertex 2 has n minus 2. Vertex 3 has n minus 3. I can actually prove this by induction if you really want to. I don't, so I'm not going to. Now, most of the time, when I ask people to draw K4, they draw a square with an X in the middle. Did any of you actually draw that for K4? Why did I draw it this way? Promise there's a reason. It's not just me being a pain in the ass. The edges don't cross each other. The only place two edges touch is at a vertex in this picture. If I drew an X in the middle, it would look like there's another dot there sometimes, depending on how sloppy you are. I tend to screw that up all the time, which is why I don't make my vertices solid dots. I make them big circles when I can. So it's obvious that here, that's a vertex. Here, that's just a crossing. It turns out there is no way to draw this picture without crossing. If we get there, we'll see that in chapter 9. So I now have three categories of graphs. I have paths and cycles and complete graphs. Pn, Cn, Kn. Given any graph, I can take its complement. I think we defined this last time. Did we talk about complements already? I think we did, but I don't remember 100%. I thought I mentioned it. I might not have. Here is a graph on 4 vertices. The complement of this graph replaces all the edges that are there with edges that aren't there. So if this is my graph G, then the complement of G could be thought of as starting with a complete graph and taking away these edges. The edges in the complement take all possible edges and throw out the ones that were in the original graph. I did this on a graph of size 3 and order 4, 3 edges, 4 vertices. What's the complement of a complete graph? Almost. Just the vertices. The graph isn't empty. I still have the vertices set, but the edge set is empty. This theorem, if a graph is disconnected, its complement is connected. The converse of this is false. If I take a graph that's connected and I take its complement, must the complement be disconnected? No. It doesn't have to be. Could it be? Yes, there's an example where it is. But I can give you a graph Here's a graph G. What's its complement? Remember, there are 6 total in the graph on 4. Both of those are connected, aren't they? So if graph is connected, then its complement might not, or it might. There's one that isn't, there's one that is. But if this is a theorem, I should be able to prove it. And again, this is a short proof. So I should do it. Now, if my graph is disconnected, what does that mean? This graph is disconnected. It's got 4 vertices and 3 edges, but this graph is connected. It's got 4 vertices and 3 edges. So that's not always true, unfortunately. We called a graph connected if I could get from place to place, right? So if it's disconnected, there's places that there's no path. There's at least one pair of vertices with no path between them at all, which means there are components, right? We talked about components in different places. So G has at least 2 components. Now let's look at the complement. I know that those vertices are the same as the vertices in G, right? The vertices in G bar are the same as the vertices in G. What do I want to show? What am I trying to prove? Aha, but not just where there's no path, but every, right? Because the goal now is to show that this is connected. And to show that it's connected means that any 2 vertices have to have a path, whether it's one edge or more, right? So pick 2 vertices. Now, you have components, right? There are only two choices. When you pick these vertices at random, they're vertices in G as well as in G bar. So if I think of them as vertices of G, they're either in the same component or they're in different components, yes? Okay. Two cases, two options. Which do you want to do first? Same component or different components? Okay. So case one, in G, U and V are in different components. Well, that guarantees me that there's no edge between U and V. They're in different components. Not only is there no edge, there's no path. That means there's definitely not a path of length 1. But if that edge UV is not in the edge set of G, then UV must be in the edge set of the complement. Because remember, the complement replaces the edges that weren't there. That edge is not there. That means UV is in the edges of G bar. That means there is a path from U to V. As a matter of fact, it's a path of length 1. Ta-da! Check mark. Case 2. This was case 1. Case 2. In G, U and V are in the same component. So U and V both live in the same blob. There might not be a direct path from U to V of length 1, but there is definitely a path because they're in the same component. And that's what it means to be in the same component. Those are the pieces that are all connected to each other. So how do I look at the complement and find a way from U to V? There's another vertex over here in this other component. So let's use that like we did here. And this time we do it twice. If U and W are in different components, then that edge is not in the set of G. V and W are in different components. It's not in the edge set of G. As above, UW is not in the edge set of G, and VW is not in the edge set of G. Therefore, UW and WV are in the edge set of G complement, which means I have a path. A path from U to W to V. Hey, wait a minute. You know what that means? That means the maximum possible distance between two vertices in G bar is 2. In case 1, the distance was 1. In case 2, the distance is 2. The complement of a disconnected graph is a graph whose diameter is very small. The biggest path we have in this graph is length 2. Sorry, the biggest distance, biggest, shortest path. Questions? Components are a way of grouping vertices. This pile are all connected to each other somehow. This pile are all connected to each other somehow. What if I have a connected graph and I still want to try and divide up my vertices somehow? I'm going to call a graph bipartite. If I can break its vertex set into 2 subsets, 2 disjoint subsets, a partition, so that the only edges in the whole graph go from vertices in one of the partition cells to the other partition cell. So one way to think of this is to think of coloring the vertices, red and blue. All of my edges have to connect a red thing to a blue thing. There can be no edges from red to red. There can be no edges from blue to blue. So I have a partite set U and a partite set V. All the edges go from UI to VI, never U to U, I'm sorry, W, U to U or W to W. Several of the graphs we've already seen are bipartite. Several are not. So consider C4. The cycle of order 4. I claim this is bipartite. How would you color those? How would you divide them up into U's and V's? Sorry, U's and W's. But if these 2 are in U, then there's a vertex edge to edge that goes from U to U. And I want all of my edges to connect a vertex in U to a vertex in W. So let's start with that assumption. I'm going to make this top left one U1. But then the top right cannot be a vertex in U, and the bottom left cannot be a vertex in U. So this is going to be W1, and this is going to be W2. And then I look at my last vertex, and what should I number it? Label it U2. Then my 2 sets are the diagonals. And all edges go from a U thing to a W thing. A partition is a dividing into subsets which do not overlap and cover the whole set. So I covered every vertex, and the set U and the set W do not overlap at all. Same question. Try C5. What happens? You can't do it, or no one can do it. That's a very distinct statement. I don't think it can be done. Why not, please?
You start with one at the top, you can go say
Red, blue.
the next one be red. That's blue, then that's red, and then you go red.
And because this is a rotationally symmetric picture, it doesn't matter where you start. As you start going around saying, well, like, this is red, so that can't be red, so that can't be blue, so that can't, you're forced, when you get to this last one, into the position where it can't be either color. That's exactly the reason. The fact that this is an odd cycle prevents it from being bipartite. But wait, there's more. Any odd cycle of any length, a triangle, a pentagon, any odd cycle will prevent your entire graph from being bipartite. So not only does C5 become untenable, K5 becomes untenable, because C5 is inside of K5, isn't it? The outside ring. Any graph that contains a triangle anywhere in it cannot possibly be bipartite. Now, this theorem has a much longer proof, so I'm not going to do it. But I think this proof is worth reading. So I know it's not a homework problem, but read this one. I think this is the 112, and I think it's worthwhile because you see the way in which we go about saying, oh, I'm stuck no matter how I go to color this. I can't do it with just two colors because of distances. And the distance being odd becomes the problem. Questions? Well, I would say the use of bipartite comes in things like communication protocols. So examining, can I go back and forth? Can all my channels go across? I can also look at what connectivity I have as I look at the bipartite behavior. Matter of fact, I can go further. I can look not just at bipartite, but tripartite, 4, 5, 6. I can say, can I color this? Can I break this up into certain subgroups of certain sizes? And I can ask how well they're connected. We're going to call those two partition cells the partite sets. So if a bipartite graph with partite sets U and W, those are the vertex sets, has every vertex in U adjacent to every vertex in W. So I'm kind of gluing my definition together. I want it to be bipartite, but I also want to have all the possible edges I can have. That's a complete bipartite graph. In which case, we'll pick one of the sets and tell me how many things are in it. So let's say I had 3 on one side and 2 on the other. So I could say a complete graph with 3 on one side and 2 on the other. So that would look like this, right? 3 on one side, 2 on the other, but everything over here is connected to everything over there. By the way, what does K23 look like? Just flip the two sides. Big deal. In general, we talk about KST. S things in one set, T things in the other. Almost always I write S as the left set and T as the right set. I don't care. You can write them as top and bottom if you want. Doesn't matter. If one of those numbers is 1, what's that graph look like? Say again? Okay. But there's another vertex, right? There's 1 on one side and 5 on the other. Yes? But remember, the way in which I draw these doesn't really matter, does it? So I'm going to change this picture just a little. The 1 is in the middle and the 5 are around the outside. We're going to call this a star. Now, I have lots of choices as to how I draw and connect my partite sets. So a lot of different visuals are possible. On page, wrote it down, 23, yes, we have a tripartite graph. K222. Set number 1, set number 2, set number 3, and everything is connected to everything else. Across the sets. So notice these two are not connected to each other. These two are not connected to each other. These two are not connected to each other. 1, 2, 3. Another tripartite graph. I don't care how many distinct partite sets you want. We can do it based on however many partitions we have, right? So if I had, I don't know, 15 possible vertices, I could partition them up a whole bunch of different ways. I can combine graphs together. So let's suppose I had two graphs, any two graphs you want. I could take the union of these two graphs, right? And just say, here's G, here's H, ta-da! I'm now going to call them one big graph, G union H. That's just like taking the two separate pictures and putting a big box around them and drawing them side by side and saying, there you go. I've connected these, I've unioned these two together. I've made them one. But this really just makes a graph with more components. Component one is however many components were in G, and then however many components were in H. On the other hand, I could add them. Now, somebody in set theory decided that what they wanted to do was to call this a join. I'm perfectly happy calling it a sum. But what this is this is G union H and edges joining vertices in G to vertices in H. So if I had G being, I don't know, a triangle, and H being a square, then the join has to add a whole bunch more edges, doesn't it? How many? How many more edges have to be put in there to make a join? Pick a vertex in G. Top, bottom left, bottom right. Pick one. Then all of those have to be connected to each vertex in H. 1, 2, 3, 4. But I also have to do that for each of the other vertices. I'm going to have to add 12 more total edges. 1, 2, 3, 4. 1, 2, 3, 4. So adding, joining, is a matter of physically connecting my two graphs. I can multiply graphs. The Cartesian product. You can do the Cartesian product in two different ways. I still have to do it to everything. If I had more components, I'd have to connect all of G to all of the components in H. I wouldn't have to connect components in H to each other. I don't have to go from G to H or from H to G. To make a Cartesian product, take all of the corners in one of them and replace it with a copy of the other. Let's use our triangle and our square again. So if I want to do the Cartesian product of these two, I can do it two different ways. I could either take 4 triangles. These are my copies of G, right? And I arrange them in this square. Top to top, top to top, top to top, top to top. Bottom left, bottom left, bottom left, bottom left. Bottom right, bottom right, bottom right, bottom right. Or I take the triangle and I put a square in each corner. And I connect all 4 corners of the squares together. By the way, you've done this already. You just didn't think about it. When you draw a square, what you're really doing is you're taking 2 paths and connecting them to each other. So you took a path and replaced each one by this. So if this is P2, this is P2 times P2. What if I did it again? P2 times P2 times P2. Well, then I get a square and another square. And I'd connect those. What the hell shape is that? Except for my lousy art, that's a cube. Qn is P2 to the nth. Q3, Q2, Q1. Q4 is called a hypercube or a tesseract. That has nothing to do with the Avengers or the Transformers. I got to remember which franchise it is. I hope you all have a wonderful rest of your day. I will see you all